Hello everybody, welcome to Coding Shastra. This single tutorial is going to be everything you need to run computer vision on steroids inside tiny edge devices. In this video, we will cover Introduction to Edge Devices, YOLO and C++, dependency setup, compiling OpenCV, compiling NCNN, C++ project setup, Colab training, integer 8 quantization, and code walkthrough of the actual object detection code, which is going to be a bonus part for this video. Before we jump into the actual tutorial, give me a minute to explain why I decided to make this tutorial. I did a deep search across the internet, but I couldn't find any reliable, up-to-date tutorials that show how to truly optimize the inference for edge devices, especially the best practices needed to squeeze out every last millisecond of performance. So I decided to make one myself. With that said, let's dive straight into the tutorial. Introduction to Edge Devices. Before we move ahead, here's a quick intro to edge devices. Edge devices are small, low-power computers that run tasks locally instead of depending on heavy cloud servers. They are called edge devices because the computation happens at the edge of the network, right where the data is produced, and usually with limited hardware. They are common in IoT systems, robotics, and embedded applications. SBCs, single board computers like the Raspberry Pi series, NVIDIA Jetson boards are great examples. For this tutorial, I'm going to use Raspberry Pi 4, which is equipped with 2 GB of RAM. It has quad-core ARM Cortex-A72 processor which runs at 1.5 GHz, and I won't overclock it. Also, I'm not going to use any external cooling. Now that we know what we are working with, let's see why we are choosing YOLO and C++ for this project. YOLO stands for You Only Look Once, because the model processes an image in a single forward pass, predicting all the bounding boxes and classes at once. This makes it extremely fast compared to older detectors that scan the image multiple times. For this tutorial, we are going to use YOLO11N, the nano variant of the latest YOLOv11 release. It's small enough to run on a Raspberry Pi 4 while still providing a solid performance. Now, why C++ instead of Python? Well, because C++ is a god. And you don't really question God. The real reason we are going to use C++ is for performance. C++ provides us much lower overhead than Python, tighter control over memory, and access to faster backends like Vulkan or other ARM-optimized inference paths. Okay, enough theory. Now let's get into the first practical step of our tutorial. Like any standard setup, we will first prepare our Pi with the necessary system packages with the help of sudo apt update and sudo apt upgrade. Once this is done, we will install few essential development packages using apt. This includes tools like CMake, Git, compiler toolchain, and other important libraries like Vulkan and OpenMP. Before moving on, we will also check the Pi's EEPROM for updates. The EEPROM stores the Pi's bootloader and low-level firmware, and keeping it updated is always recommended. Newest versions often include better stability, improved memory handling, and more efficient resource management. This is basically everything that matters when running heavy inference on limited hardware. Now we will go ahead and reboot the Pi. Now that the Pi has rebooted and is fully prepared, we can dive into more complex dependency setups. One of the major components that we need is OpenCV, which handles all the image processing steps around our computer vision pipeline. So now, we need to build OpenCV from source. Installing it via pip or pre-built packages isn't enough because we need performance optimizations for the Raspberry Pi and access to specific headers that are often missing in the packaged versions. Before building OpenCV itself, we first install its required dependencies. So we start with sudo apt update and then install the OpenCV build dependencies using apt. Once that's done, I will create a project directory called YOLO NCNN and inside it another folder called third party. This is where all the external libraries like OpenCV and NCNN will exist. Next, we need to download the latest OpenCV release, which is 4.12.0 along with the matching OpenCV contrib modules. After extracting them, we rename the folders to OpenCV and OpenCV underscore contrib to keep the paths clean. Now we can finally build OpenCV. Inside the OpenCV directory, we create a build folder and then run cmake configuration command inside this build folder. This command is long and I strongly recommend not modifying these flags unnecessarily. Even small changes here can lead to unpredictable build errors or runtime issues later, especially on ARM-based systems like the Raspberry Pi. Some of the critical flags from this command related to Pi optimization are NEON, which enables ARM SIMD instructions for faster vectorized math. OpenMP, which allows OpenCV to utilize all the 4 CPU cores. TBB is Intel's task-based parallelism, enabled here mainly as a fallback. OpenMP does most of the work here. L-Atomic is required on ARM to support atomic operations used by OpenCV. Also, components like tests, examples, GUI, and Java bindings are disabled to reduce build time and also the memory usage. Once the CMake files are generated, we move on to compilation. Compiling OpenCV is a memory-intensive task. On Pi, especially the 2 GB RAM variant, the build can fail or even crash without enough available memory. To stay safe, we temporarily create a 4 GB swap file. This swap exists only until the next reboot and provides enough virtual memory to complete the build reliably. Now you can verify the available memory using the command free space -h. This will show the total memory available including the swap partition and actual physical memory. Now let's compile OpenCV with make space -j4. The J4 ensures all 4 CPU cores are used. If your Pi becomes unstable or crashes, reduce this to J2 or even J1. Finally, we will install OpenCV system-wide and refresh the linker cache. So we will now run sudo make install and sudo ld-config. The build process can take anywhere between 1 to 2 hours depending on the Pi. Once this step completes, OpenCV is fully built, optimized and ready to use. With that done, we can now move on to building NCNN, which will handle the actual neural network inference. NCNN is a lightweight neural network inference engine developed by Tencent. It's highly optimized for ARM-based devices, which makes it ideal for platforms like the Raspberry Pi and even Android phones. We are already inside our third-party directory. So let's start by cloning NCNN from its official GitHub repo and then cd into it. Once inside the NCNN directory, we do git submodule update init. This command initializes missing submodules and pulls the exact version required by NCNN. This step is extremely important. Skipping it can lead to runtime errors later, forcing you to rebuild NCNN entirely from scratch. The key submodule here is GLSlang, on which NCNN relies internally. After that, we go back to the parent directory and create a separate build folder called NCNN build and then cd into it. Now we generate the build files using the cmake command. This step is quick and usually takes less than a minute. Once the build files are generated, we compile NCNN using make j4. Now again, as I said before, if the Pi becomes unstable or crashes during this compilation, you can always change J4 to J2 or J1. After compilation finishes, we install NCNN system-wide using sudo make install and sudo ld-config. At this point, you would expect everything to be ready. But with NCNN, that's not entirely true. By default, NCNN does not place all the required headers and libraries in locations where the compiler and linker can find them. This can lead to confusing runtime or linking errors later on. So we will fix this manually. While still inside the NCNN build directory, first we will create an NCNN folder inside user local lib, and then we will recursively copy all the header files from install include NCNN into user local include. We also copy the static library libncnn.a from install libncnn into user local libncnn. Once that's done, we run sudo ld-config for one last time. Finally, we will verify that net.h exists inside user local include ncnn, and also libncnn.a exists inside user local libncnn. These two expose the core NCNN API and also confirm that NCNN is correctly installed and is ready to be used inside our project. With NCNN built and installed, we are now finally ready to write our code. So first, let's go inside the root directory of our project, which is YOLO NCNN, and let's create 3 directories called data, src and build. Then we will also create cmake list.txt at the root level. You can copy or directly clone the contents of the txt from my git repo. Now let's cd into the src directory and create a source file named YOLO11.cpp. Again, I am directly pasting the contents from my git repo itself, and you can also do the same. Now let's go inside the build directory that we created just now. Here we will generate the build files for our project, and once that's done, as usual we will compile our project using make j4. So as you can see, the build completed with no errors, and thus our code is ready to run YOLO based object detection on our Pi. So now our code needs a YOLO model to actually run object detection. Instead of using a generic pre-trained model, we will use a custom trained and optimized YOLO11N model specifically adjusted for resource constrained devices like our Pi. I would suggest sticking with me till the end of this section because the choices we make here directly decide whether inference on the Pi feels slow and unstable or fast and practical. So now let's head to Google Colab. So this Colab notebook here will be uploaded on the GitHub repo. Once you have opened the notebook, the very first thing that you want to do is go to runtime, then select change runtime type, then select T4 GPU and then click on save. Once that's done, just go here and click on connect. So this enables GPU acceleration for our training process and thus increases its speed. Now we need few Python libraries. So first we will install Ultralytics, which is the official YOLO library. The second library that we need is 51. This library will help us to prepare and download the dataset for our training process. Next is OpenCV Python for image handling, and the last one is Matplotlib, on which some libraries rely internally. So once we have installed the required libraries, we can now move ahead. Now here's an important decision choice. I want my YOLO model to detect only humans and nothing else. So instead of training on all the Coco classes, we filter the dataset to include only the person class. This is very important optimization as the model becomes smaller and faster, thus improving the overall inference and accuracy. If your case also involves detecting only one or few object types, then retraining like this is strongly recommended instead of using a general purpose pre-trained model. Okay, now the very first thing that we want to do is download the dataset. So we will download three splits of the dataset, which are train, validation, and test. As you can see here, we have explicitly set the person class, so the downloaded dataset will only contain images of humans. Each split of the dataset will be stored under the path datasets Coco underscore person underscore YOLO. So effectively, what we are doing in this block of code is we are downloading the well-known pre-trained Coco 2017 dataset filtered only to humans. So this will take a considerable amount of time to download the complete dataset, and once that's done, we can move on to properly formatting this downloaded dataset. So this block of code here reorganizes the dataset into the exact directory structure expected by YOLOv11. This small script here simply moves the images and labels into the proper train, val, and test folders. At this point, I strongly recommend downloading the dataset locally. Colab runtimes can disconnect, and if that happens, you lose everything. So we compress the formatted dataset into a .7z archive and then we download it. If the auto download does not start, then open the Files tab here. Click to the three dots next to the archive file and then download it manually. Later on, instead of re-downloading the dataset, you can upload the locally downloaded .7z archive to Google Drive and then copy paste the link here. This command here will then download the .7z archive into the Colab runtime, and then this following command will extract that archive. If you have extracted the dataset from the archive with the help of this command, then there is no need to run this block of code as the extracted dataset is already in the required YOLOv11 format. Now once we have our dataset downloaded, the last step of preparing our dataset is creating a YAML file. This file tells YOLO where the train, validation, and test images are located, and also what classes exist in the dataset. So as you can see here, we have specified the exact locations of the train, validation, and test splits of the dataset along with the class that exists inside our dataset, which is the person class. So this will go into the contents of the .yml file, and the YML file will be stored at this path. Once this is done, we are now ready to actually train our model. Now comes the main training step. First we will import YOLO from Ultralytics, then we will load the nano variant of the YOLO11 model, YOLO11 N.pt. Once that's done, we will start training our model with the help of model.train. One important parameter here is IMGSZ, which I have set to 480. YOLO11N normally expects an input image size of 640 by 640, but we have reduced it to 480 by 480 to improve the inference speed on the Raspberry Pi. So that's why we have passed 480 over here to the IMGSZ parameter. We also set the device parameter to 0, so the training process will use the T4 GPU made available to us by the Colab runtime. The remaining parameters are standard training settings. So for me, the training process took about 1.665 hours, so roughly about 1.7 hours on the T4 GPU. If you are using a paid Colab plan with a more powerful GPU, then obviously this will finish faster. Once the training is done, then we validate the model and check its mean average precision. So as you can see, I have got an MAP of 0.418, which is approximately 0.42, which is very good for a nano model, especially with a reduced image size. Finally, we run predictions on few test images to make sure that the outputs make sense, inference isn't unusually slow, and there are no obvious issues. And as you can see from these results, everything seems to be completely fine. Now we have trained our model, but we still can't directly use it on the Pi. So first we will reload the trained model from this path, and then we will export it in the NCNN favorable format using model.export. Here I have set the half parameter to true, so the model will be exported as FP16 instead of FP32. And this is important since we need our model to be smaller as well as faster with limited resources. While the model is exported to NCNN format, internally first it is exported to ONNX format and then it is converted to NCNN format. So once this step is done, we need to download the model locally, and that means we need two files, .bin and .param. The path to these files can be found in the result. Here as you can see, this is the path to .param file and this is the path to .bin file. Once this is done, the model can now used with our C++ code. So in this section, what we have effectively done is we have stripped the model down to only the classes we care about and retrain it at a smaller input resolution, both of which massively reduce the computation during inference. These two changes alone make the difference between a standard YOLO model that struggles on the Pi and this custom trained model that runs fast enough to be practically usable. Next, we will push this even further using int8 quantization. Now let's talk about integer 8 quantization. The simplest way to understand this is if I ask you to multiply two floating point numbers, say 2.12 and 4.14, you will get a very accurate result, but it takes more time and computation power. If you instead multiply just the integers of these two numbers, which are 2 and 4, the result comes much faster but with a small loss in precision. That's essentially what integer 8 quantization does. When we quantize the model, at a high level, we convert the 16-bit floating point values inside the model into 8-bit integers. This makes the model significantly faster and lighter while sacrificing only a tiny amount of accuracy, which is usually acceptable for edge devices like the Pi. Now, to perform integer 8 quantization properly, the model needs to understand the range of values it will see during the inference. That's why we provide a calibration dataset. It helps NCNN map floating point values to integers safely without breaking the model. Now, for the int8 model to work well, the calibration images must cover a wide range of real-world variations, different poses, lighting conditions, scales, and backgrounds. Since our task is human detection, the calibration data should represent humans in diverse scenarios. To achieve this, we will take 70% of the images in our calibration dataset from the training split and 30% of the images will be taken from the validation split. The images are randomly selected from both the splits to avoid any bias in the calibration process. We then merge the images from both the splits into a single image list called calib_images and then again shuffle this list. Once this is done, we will copy all the images from this list into a single directory. Now the path to this directory is specified in the variable calib_dir, and so we will copy all those images to this path. Now once the images are copied to the required directory, we will create a .txt file called calib_list.txt. This .txt file simply contains the absolute path to all the calibration images and is required by the NCNN's quantization tools. Once we have prepared the calibration dataset, we will zip the entire directory containing this dataset into a .7z archive. We need to download this archive and then transfer it to our Raspberry Pi, since the calibration will be done on the Pi with the help of previously compiled NCNN library. So before closing the Colab, make sure that you have downloaded the .param file specified at this path and also the .bin file which is specified at this path. Along with this, you will also need the .7z archive of the calibration dataset that we just talked about. So I have downloaded all the required files, and the first thing I will do is extract the .7z archive. Now we need to transfer these files to the Raspberry Pi. For that, I am using WinSCP, which is a really simple and reliable tool that transfers files over SSH using SCP protocol. Before copying anything, let's create a few directories on the Pi. Inside the already existing data directory, I will create two folders, models and calib_images. Back in WinSCP, after refreshing the view, I will go into the models folder and paste the downloaded .bin and .param files of the model. Next, I will go into the calib_images directory and paste all the extracted calibration images along with the calib_list.txt. Once that's done, we are ready to quantize the model. Now let's head back to the Pi's terminal. The very first step is to optimize the model, and we do that using NCNN optimize. This generates a new set of files with -opt in their names, which are internally simplified and better suited for quantization. Next, we generate the int8 quantization table. Here's what happens internally. NCNN reads the optimized model files and all the calibration images listed in calib_list.txt. Using this data, it produces a file called model.table, which stores all the scaling factors required for the int8 quantization. One very important thing to note here is parameters like mean, normalization, input shape, and pixel format must exactly match the pre-processing used during inference. Even a small mismatch here can significantly hurt the accuracy. Now we quantize the model using NCNN to int8. This command takes the optimized model and the quantization table to produce model int8.param and model int8.bin. These are the final int8 quantized model files. If we ls into the models directory now, you can see that all the required model variants are present. With int8 quantization done, we have pushed the model as far as possible for edge deployment. So now let's actually run inference. For testing, I will use the classic bus.jpg image. We will go into the project directory, which is YOLO NCNN/build. Now first, let's run inference using the custom trained 480 by 480 FP16 model. The program arguments are first path to the image, then model path. The code automatically appends .bin and .param to the path here. Third, optional flag to specify whether the model is int8 or not. Since this is not int8, I will pass 0 here. So as you can see, inference took 202.70 milliseconds and post-processing took 6.19 milliseconds. The output is saved as output.jpg inside the build directory itself. So as you can see, it has done a really great job. It has detected 3 people with good accuracy. Next, let's try the optimized FP16 model. Now the inference time drops to 186.21 milliseconds, with post-processing taking only 0.71 milliseconds. Again, let's go and check the output.jpg. Yeah, it has detected 3 people with pretty good accuracy. Now let's try the int8 quantized model. This time we will pass 1 as the int8 flag. On the first run, the model detects 0 persons, which is obviously incorrect. Int8 models usually don't give wildly wrong outputs, so let's run it again. On the second run, it detects 2 persons. To be sure, let's run it one more time. And again it detects 2 persons. Okay, so the model works fine. The inference time is now down to 168.8 milliseconds with post-processing around 0.73 milliseconds. So if we compare the optimized FP16 model and the int8 quantized model, int8 saves us roughly 18 milliseconds of inference time but at the cost of one missed detection. Let's view the output.jpg of the int8 model too. As expected, the missed detection is the person who is partially out of frame. If needed, you could tweak the confidence and NMS thresholds, which are additional optional arguments to recover the missed detection. So int8 quantization does improve performance, but in this case and as well as some other cases, the gain is relatively small while accuracy becomes less stable. For this specific setup, FP16 with optimization already offers an excellent balance between speed and reliability on the part. So for you, if the inference latency matters a lot, then you can go ahead with int8 quantization, but be sure that you will have to sacrifice some tiny amount of accuracy. Now before we wrap up the video, I've added a small bonus section. If you want to understand what's actually happening inside the code at a high level, this section is for you. So here is the code. At the top, we have included few standard C++ headers, OpenCV, and most importantly, net.h and layer.h. These two headers provide all the core NCNN classes and APIs needed to load the models and run the inference. Next, we define a simple object structure. This is used to store the results of detection. The bounding box as an OpenCV rectangle, the class label, and also the probability of the detection. Now let's jump directly to the main function of the code. So this is the main function. The program expects at least 2 arguments, the image path and the model path. Optionally, we can also specify whether the model is int8 quantized, the confidence threshold, and also the NMS threshold. If these optional arguments are not provided, the default values to these arguments will be used. After that, we load the image and do a basic sanity check to make sure that the image was read correctly. We then define a vector called class names. Even though our model is trained only for the person class, I have kept all the Coco label list here. You can safely remove the unused labels if you want to slightly reduce the memory usage. Finally, we create an instance of YOLOv11 class, call the detect function, and then save the results using this save_result function. That's all main does. It mainly acts as a clean entry point and argument handler. Now let's move on to YOLOv11 class, which is where the real work happens. By default, we enable Vulkan as backend. On the Raspberry Pi, this significantly reduces the inference time compared to the CPU-only execution. This line here tells NCNN to use Vulkan for computation. Next comes a very important Pi-specific detail. We enable BF16 storage by default. Internally, BF16 or 16-bit brain floating point uses the same memory size as FP16 but with a wider exponent range which improves numerical stability. Internally, BF16 or 16-bit brain floating point uses the same memory size as FP16 but with a wider exponent range which improves numerical stability. scalability. Without this enabled, the inference pipeline can fail even when using int8 models. Now, if the model is int8 quantized, then we explicitly enable int8 inference and disable FP16 arithmetic. Otherwise, FP16 arithmetic is enabled for faster computation. We also enable packing layout, which allows NCNN to take advantage of ARM Neon vector instructions. Finally, we configure NCNN to use all 4 cores on the Pi and then load the model parameters and weights. After that, here is the main detect function that actually detects the objects. In this function, we first define the target input size, in our case which is 480 by 480, which matches how the model was trained. We then read the original image dimensions and then compute a scale factor to resize the image so that its aspect ratio remains intact. This avoids distortion to the input image. During this step, the image is also color corrected and then resized. After resizing the image dimensions may not be perfectly aligned with the network stride. So we pad the image so that both the width and height becomes multiples of 32. This is required by the YOLO's internal feature map structure. The padding is added symmetrically using a constant value of 144, which is the standard padding value used by YOLO models. Once the image is resized, we normalize it. Pixel values are scaled from the range of 0 and 255 to 0 and 1 by dividing by 255. We then create an NCNN extractor which is responsible for executing the model. The pre-processed image is passed to the extractor using the input blob name, and then we extract the output tensor from the output blob. At this point, the model has completed inference and produced raw YOLO predictions. We also measure the inference time to track performance. Now here, as you can see, the raw output tensor is passed to a custom parser function. This function decodes the bounding boxes, extracts class confidence scores, and filters the predictions using confidence threshold. This function then properly pushes the detected objects into the object structure list. We then use quicksort to sort all the detections in descending order using their confidence scores, and then apply non-maximum suppression, which removes the overlapping boxes and keeps only the best ones based on the NMS threshold. Now, since the image was resized and padded previously, we undo these transformations. So each bounding box is unpadded and then rescaled back to the original image size and then clamped to stay within the image boundaries. This ensures that the detections align correctly with the original input image. The results are then saved to same object structure list. Finally, we log the inference and post-processing time and exit the function. Also, here is the save result function. This function does nothing but takes those detected objects and draws a bounding box around them in the image and also writes the label of those detected objects and their confidence scores. Finally, it saves the image as output.jpg. So that's it for this tutorial. As Richard Feynman once said, "What I cannot create, I do not understand." And that's exactly what this whole video was about: building, optimizing, and understanding the full pipeline end to end. If you have any questions or want to dive deeper into any part, feel free to drop a comment below. I will see you in the next tutorial.